In this video, we're going to explore numerical methods of approximating the solutions of ordinary differential equations, because for the most part, we can't solve them with the other methods we have used so far in this class. So, suppose we have this derivative with respect to x, dx dt, which is a function of both t and x. And we've got some initial condition, and we want to approximate the solution near t equals t naught. Now, if we use the methods that we have learned in calculus, we know the equation of the tangent line x is going to be equal to the slope t minus t naught plus x naught, where the slope is the derivative, and we're defining the derivative as dx dt evaluated at t equals t naught. Then we're going to get this tangent line, and here's our solution, and we're going to get an approximation, right? Now, if we continue to do this approximation after the first and second iteration, we keep iterating, and you can see when we're doing this approximation, we're just keep doing these iterations, and we end up having something that looks like this. Here's where we start, then we're going to choose another x sub 1, and then an x sub 2, then an x sub 3, and we're just going to keep iterating through there. So there are times in which I can find the x of t naught plus h being the difference between one t and the next t, that's the h, by a Taylor series. This is a nice Taylor series, where h is equal to the change in x, in other words, from this point to this point, this delta t or h. One of the algorithms, and there's calculators for these, to do this approximation is Euler's method. Here's one of them. Now there's actually going to be 3 of them that we're going to explore. If you're going to use one of these calculators or any calculator, make sure you're using the correct one. This is Euler's, is the one I'm going to use. And I can go to Wolfram, or I can click on this one. I'm going to go out to this one, and I'm going to show you what you need to put in to be able to solve this initial value problem, where I've got y prime plus 2y is equal to 2 minus e raised to the negative 4t, where they give me the initial value. They also tell me to use Euler's. They tell me what my h needs to be, and then these are my t's that I'm looking at. Now notice I don't have a t naught. T naught would be, because my h is 0.1, my t naught must be 0, because I have this t sub 1 minus my h, which gives me, in this case, would be t naught. So I'm going to show you what you're going to put into this. One I'm going to look at is this emathhelp.net calculators, differential equations, Euler method calculator. It's just what I'm going to use this time. And I'll show you everything that you're going to need to put in. So I just want to show you what I got when out to that website, eHelp. So I'm just going to bring these pictures in. And this is what I put in. So notice I have to put in the function solved for the derivative. So it's a function of t and y. So I solved for my function. My function was given to me as y prime plus 2y is equal to 2 minus e raised to the negative 4t. And so I had to bring this 2y to the other side, so it's a minus. My h was a 0.1, so that's that piece of it. And we talked about how my t naught was 0, so that's that piece of it. My y naught, that's this piece. That's a y naught is equal to 1. And then the t sub 1, where are we ending? Well, I'm ending right here. This is where I want to end. And so this is what I put into that calculator. Now I want to show you what came out as answers. So you see that these are the first set of answers. These are the solutions, and it's going in by step. So step 1, 2, 3, and then of course I get down to step number 5. That is my last step. And then I end up with the answer as well. And so here's my answer. So y of 1/2 is approximately equal to 0.5 0.167737. Now, when you're going through this, the step size, if you decrease the step size by a factor of 10, your error will also decrease by a factor of 10. There are two different kinds of errors when solving differential equations numerically. First is a round-off error. We are going to get that, especially if you round off too early or you round off so it's not a long enough set of numbers. The other is a truncation error, and that's caused from dropping all but the first two terms of the Taylor series. And it's seen when using the approximation here. Excuse me. So this is how we're going to define the error. The error of order n, denoted with this funky looking O, delta t to the n, is an error which approaches a constant times this delta t raised to the n as delta t goes to 0. So in other words, the smaller your step size, the more the error goes to 0. Now, if you're interested in doing information about the error, there's this book here. It's called Differential Equations, a Dynamical System Approach, Part 1. Euler's method's fairly nice at approximating nice solutions that don't change very rapidly, but that's not always true. Not all solutions are going to be well behaved. Now, there is second-order numerical methods called the improved Euler's method and Huon's method. These also do a stepping through. Notice how the formula is slightly different, and this is why it's called a second order. If you take a look at this one compared to my previous one. And here's the algorithm for it. Like, I want to do the algorithm. And you can go to two places. You can again go to this eMath Help Calculator, Differential Equations and Improved Euler's Huon Calculator. Or you can go to Wolfram Alpha, either one. And you would type this in just like we did before, like I showed you before, using that y prime has to be set to itself. So you're going to have the y prime, so it's isolated, so it's negative 2y plus 2 minus e raised to negative 4t. Your y sub naught is 1. That comes from here. Your t naught is going to be this first number that's listed minus your delta t, which is your h, so that's still going to be 0. And then, of course, you're going to put in your last, which is 0.5. Another way to, another method of a numerical method is the Ranjicata method. This also has a nice algorithm. You can search for the Ranjicata method, or you can go to Wolfram Alpha. And then, of course, you can also just search for it. I like Wolfram Alpha to use it, especially if you want to find the exact values compared to the numerical. Wolfram Alpha will give you that. Not all of them, not all the calculators will give you that. And that's pretty much it for this section. So make sure you bring your calculator or your computers tomorrow, because we're going to be using computers to solve these, because we're not going to do this by hand. And that's it.